we go. It is the last day of new material, yay! You can be excited, you're allowed. You're very allowed to be excited this time around. I promise, last day of new material. Homework questions, for which I do not have my book, but it's somewhere. Anything for homework questions, which we decided is due on Friday from 5.4 and 5.6. Anybody, anything? No good? Okay. Remember then, tomorrow and Friday is review group work. I will get that up and posted on Moodle shortly before class. Tomorrow, the first part, and shortly before class on Friday, the second part. Entirely up to you if you want to sign in. I would highly recommend it. We've got an hour. You've got nothing else going on, so you might as well use the hour to get some of your review group work done. And the review group work is broader than the exam. So we've got that list of topics that we made last time for the final exam. I am not limiting the list of topics on the review group work. So the topics on the review group work are going to be broad over the whole course of the semester. That's kind of your opportunity to review, but in a less stressful situation than on a test. So I don't know, what else? Anything else for logistical questions before we get going with the last new material of the semester? Anything? Nobody? Okay. All right, let us review where we are at this point in time. We did it in breakout rooms yesterday. I'll do it live today. So here's where we're at. We have a differential equation, vector x prime equals vector a times x, right? Remember, this needs to be homogeneous and it needs to have constant coefficients. Those are the two requirements for using this technique in order to solve. So we want to find eigenvalues. And the way we do that is by taking the determinant of lambda I minus a and setting that equal to 0. And we want to solve for lambda. And then we want to find eigenvectors. And those are going to satisfy lambda I minus a times my vector v equals the 0 vector. Remember, we can have eigenvalues that are defective. So it's possible that our eigenvalues might be defective. These are defective if the algebraic multiplicity is greater than the number of free variables. Defective if the algebraic multiplicity is greater than the number of free variables. That's going to be defective in this case. And if not defective, then we have n linearly independent eigenvectors. We're going to call them v1, v2 through vn. And that means we also have n linearly independent solutions. And we are going to call those n linearly independent solutions x1, x2. These are vectors all the way through xn, where vector xi equals e to the lambda I t times vector vi. So that's how we make each of those vectors. That's kind of the same way that we did it with a regular normal system of equations, or regular normal equation back in chapter 2. So we've got that, and then we have our general solution, which is vector x equals c1 vector x1 plus c2 vector x2 plus a bunch of dots plus cn vector xn. We can do this with real roots or with complex roots, either way. We did a little bit with complex roots last week, Friday. Okay, if they are defective, if you have a defective eigenvalue, then we've got some question marks and we have a frowny face, and that is what we need to do today in our very last part of new material. So what happens if we have a defective eigenvalue? We are only going to deal with defect equal to 1, and the defect is the algebraic multiplicity minus the number of free variables. So the defect is basically how many linearly independent eigenvectors are you missing? That's what the defect is going to be. How far off? What's the difference between what we should have and what we actually can get? So that's your defect. We are only going to deal with defect 1. If I had one more class period, and it is more important to do review group work than to teach for one more class period, but if I have one more class period, we would do defects of higher order. And if we were in the classroom, because this is not great over Zoom. But one more class period, we would do defects of higher order. Today, we're just gonna do defect 1. Okay, I am going to stop sharing my screen, and I'm going to have you give me an indication that yes, that all looks good review. Most of the words that I'm saying make sense to you. You are remembering them, process, etc. Questions, Stuart? Yes.
On the homework last night, we just had non-defective ones, right?
Yes, yesterday was just non-defective.
Those were defective.
Yep, you don't know how to deal with defective ones yet. That's today.
Okay.
Yes. Other questions? Give me a thumbs up, tell me that all looks familiar. Cool, okay. Anything else? Other questions? Alrighty then. So let's talk about what happens when you have a defective eigenvalue. If we were in class, I would lead you through this really cool development of how this all works and show you where everything comes from. We're not in class, and I can't go back and forth with you, and it doesn't work as well. So I am just going to give you the answer. Sorry. So if you have an eigenvalue, lambda, with defect 1. Here is what your solutions are going to look like. Vector x1 is going to be v1 e to the lambda t. Vector x2 is going to be v1t plus v2 e to the lambda t. I got to tell you what v1 and v2 are, so hang on just a second. But these are my two linearly independent solutions. These are my two linearly independent solutions. Okay, here's where the v1 and the v2 come from. Lambda I minus a quantity squared times v2 is equal to the 0 vector. 3 requirements. That's the first one. Second one, lambda I minus a times v2 is equal to v1. So that's where your v1 comes from. Lambda I minus a times v2 equals v1. And third, v1 is not equal to the 0 vector, and v2 is not equal to the 0 vector. That's where we're going to get our two linearly independent solutions. Lambda I minus a quantity squared times v2 is the 0 vector. Lambda I minus a times v2 is v1, and both of these vectors that we are looking to get are non-zero. Again, if I had you in the same room with me and I could do back and forth with you, we would do the development as to where this comes from, and it wouldn't just come out of left field. I'm sorry that it's coming out of left field at this point in time. I don't have a better way to do it for you. I just don't have the back and forth to be able to show you where this comes from. It's in the book. You can read it. You can see where this is actually coming from, but I'm just making it fall in your lap today. All right, so let's do an example. Actually, two. We're going to do two examples today. I don't know that we're going to have time for a third, but let's do